Welcome, everyone. If you're a first-year biomedical engineering student joining us today, you are in exactly the right place. I am absolutely thrilled to guide you through this explainer on the absolute foundations of electronics. Today, we're not just going to memorize a bunch of formulas. No, we are going to build a deep, conceptual understanding of how electricity actually behaves right from first principles. Okay, let's dive into this roadmap. First, we'll explore the mystery of charge. Then, define the big three: current, voltage, and resistance. After that, we'll look at the historical struggle of George Ohm, introduce the math, clear up some really common misconceptions, and finally, look at energy and our next steps. We're going to build our intuition completely before we even glance at an equation. Right, let's get into section 1, the mystery of charge. Before we can even think about building a circuit, we need to understand the absolute smallest building blocks of electricity.
I want to start off by posing a bit of a curious question to you. If a battery is a source of electrical energy, why doesn't it just produce an infinite amount of current the very moment you connect a wire across its terminals? I mean, what is actually physically stopping the electricity from just flowing all at once in a massive instantaneous flash? To figure that out, we have to look much closer at what's actually moving inside that wire.
And that brings us to electric charge. So what is it, and why does it even exist? Well, charge is simply a fundamental property of matter, kind of like mass. Everything around you is made of atoms, which contain positive protons and negative electrons. In conducting materials, like a standard copper wire, these electrons are loosely bound to their constituent atoms. They're just sitting there, hanging out, waiting for a little bit of energy to mobilize them. Without these tiny mobilizable electrons, we wouldn't have any electrical phenomena, no electronics, and for sure no biomedical devices. Now, an individual electron carries a charge that is unbelievably small. I mean, so small that trying to calculate circuit behavior one electron at a time would be an absolute nightmare for any engineer. Because of this, scientists introduced a much more practical bundle of charge, and it's called the coulomb. Think of it kind of like a dozen eggs, but instead of 12, 1 coulomb is a massive quantity of approximately 6.242 times 10 to the 18th electrons. Bundling them up like this allows us to actually talk about the movement of charge in practical, everyday macroscopic quantities. Which brings us perfectly to section 2, current, voltage, and resistance. These are the big three concepts that literally govern every single circuit you will ever build. And this brilliantly illustrates the concepts we're about to discuss. Since electricity is invisible, we engineers often use the hydraulic analogy to build our physical intuition. We can basically compare the invisible electrical forces happening inside a wire to the very tangible, relatable behavior of water flowing through a system of pipes. First up is electric current, which is represented by the letter I. Intuitively, you can think of current as the volume flow rate of our water. You know, how many liters per second are moving past a certain point in your pipe. In electronics, current is simply the rate at which electric charge flows. We measure this in amperes, and 1 ampere is defined as exactly 1 coulomb of charge passing a specific point in 1 second. So current equals charge divided by time. It's the actual physical movement of those electrons we were just talking about. But here's the thing. Water doesn't just flow through a pipe on its own, right? It needs pressure, and that is voltage. Voltage is the electrical potential difference between 2 points. It acts as the driving force. Going back to our analogy, it's exactly like the water pressure created by a pump. Scientifically speaking, 1 volt is defined as 1 joule of electrical potential energy per coulomb of charge. It is the literal energy that pushes those massive bundles of electrons through your system.
Okay, so we have a push and we have a flow. But the flow isn't infinite. And hey, this actually answers our earlier question about the battery. The flow is limited by resistance. Resistance is just the natural opposition to the flow of electric charge in a material. In our hydraulic analogy, imagine a really narrow aperture or maybe a section of pipe that's filled with gravel. It acts as a physical flow restrictor, naturally impeding the water. Every single material has some natural resistance, and that dictates exactly how much current will flow for a given amount of voltage.
Now that we have a solid intuitive grasp on these concepts, let's shift to section 3, the struggle of George Ohm. Because these clean, elegant definitions we rely on today, they were actually born out of a very messy and difficult history. Picture this. It's 1825 and George Simon Ohm is just a 28-year-old high school math and physics teacher in Bavaria. He starts experimenting with electric circuits. But at the time, the batteries available were incredibly weak and totally inconsistent. They'd often just die out within minutes.
On top of that, the highly respected French scientist André-Marie Ampère had previously done some experiments using thick wires and very weak batteries. This led the whole scientific community to wrongly believe that current was largely independent of voltage. Because Ampère was famous and Ohm was, well, an unknown high school teacher, Ohm's initial discoveries were completely overshadowed and largely ignored.
But Ohm was absolutely brilliant. Because he lacked reliable electrical meters, he actually used a compass needle placed near a wire to measure current through magnetic deflection. How clever is that? Furthermore, he used first principles thinking. He drew a physical analogy between the invisible flow of electricity and Fourier's established laws of heat conduction. Ohm hypothesized that just as the flow of heat is proportional to a difference in temperature, the flow of electricity has to be proportional to a difference in electrical tension, which we now call voltage.
His persistence really paid off, which brings us to Section 4, Understanding Ohm's Law. We have the physical intuition, we have the historical context, and now it is finally time to introduce the math. Ohm's law can be written in 3 algebraic forms, but I want you to focus heavily on the first one. I equals V divided by R. This perfectly captures the causal physical meaning. Current is the result. It is the consequence of voltage pushing against a material's natural resistance. The other 2 equations, V equals I times R and R equals V divided by I, are mathematically equivalent and are super useful for finding the required push or determining a material's property when you already know the other variables.
So the crucial point is how all of these units actually tie together. We have the Coulomb, which is that massive quantity of charge. We have the ampere, representing the rate of that charge's flow. We have the volt, representing the potential energy that's pushing the charge. And finally, right in honor of our persistent high school physics teacher, we have the ohm, symbolized by the Greek letter omega, representing the strictness of the flow restrictor. Really understanding what these units physically represent is exactly what separates a great engineer from someone who just plugs numbers into a calculator. Let's see how this builds a framework for conceptual problem solving. If you are working on a biomedical device, before you write down a single number, I want you to picture the sequence. First, a battery or power supply applies a potential difference across a component. Second, that component naturally opposes the flow based on its physical geometry and material. And third, only as a resulting consequence, a specific rate of charge movement, the current, is established through the component. Its cause, opposition, and then effect. This logical flow leads us directly into Section 5, Misconceptions in Metrology. When you truly grasp the physical reality of circuits, you can easily avoid the common traps that catch so many first-year students. Here are a few of those traps to avoid. First, voltage does not flow. Just like pressure doesn't flow through a pipe, water does. Voltage is applied across a component, which causes current to flow through it. Second, resistance does not consume current. Remember, charge is a physical thing. It doesn't just magically disappear. The exact same amount of current that enters a resistor leaves it. And third, more voltage is not always better. Pushing too much current through a resistance generates a lot of heat, which can easily destroy sensitive electronics. That heat generation is described by Joule's law. As current is violently forced through a resistor's material, electrical potential energy is lost, and it's converted directly into heat. The resistance doesn't consume the charge, it consumes the energy of the charge. And this isn't just a byproduct. I mean, it's exactly how electric heaters work, and it is something you must manage incredibly carefully when designing medical circuits. Now, what's really interesting about this slide is how fundamental these classical concepts still are today. In 2019, the International System of Units was completely redefined. Historically, the ampere was based on macroscopic physical forces between wires. But today, because Ohm's concepts are so remarkably robust, the ampere is now anchored directly to the exact quantum charge of a single electron. The foundational principles you are learning right now are tied directly to the quantum fabric of the universe. Which brings us to our final section, Section 6, Energy, Power, and Next Steps. To quickly summarize our key takeaways today. Charge is fundamental, and current is its flow. Voltage is the invisible push, and resistance is the physical obstacle. Ohm's law simply binds them all together. As biomedical engineers, you're going to use this constantly, whether you're analyzing skin resistance in an ECG, calculating the required voltage for a neural stimulator, or designing the power systems for a life-saving device. You now know exactly how voltage pushes current through a resistance. But I think that leaves us with a fascinating, lingering question for our next lesson. Where exactly does that voltage come from in the first place? I mean, how do we continually generate the push required to keep a circuit alive and functioning? Next time, we're going to explore the origins of this force as we dive into understanding electrical energy and power. Thank you so much for joining me today, and I'll see you in the next explainer.